So question 4 says, draw a diagram showing 3 molecules of hydrogen chloride indicate the interatomic and intermolecular forces. So 3 molecules of hydrogen chloride, and we can't just put them anywhere. This is like some exam and homework questions, exactly the same as the example and what we did in class. So when you show these 3 molecules, you need to make sure that the opposite ends, the opposite dipoles rather, line up, because that is showing the intermolecular force. If you're asked to draw a diagram, make sure that you also include labels as to what the things are and show different lines. The intermolecular force, you can be a bit more specific here as to what type of force it is. Hannah, what type of intermolecular force do I have here?
So ionic?
No. Intermolecular force, there's one of 3 options. Katie, what type of intermolecular force would this be?
Hydrogen bonding.
No, not hydrogen bonding. Nicholas, try you. Intermolecular force that we have here.
So isn't it dipole?
Yes, this is dipole forces. Because of the partial dipoles. It's not hydrogen bonding only because this is chlorine and not one of the 3 special elements, fluorine, oxygen, and nitrogen. So just because there's a hydrogen doesn't mean hydrogen bonding. You need the hydrogen and you need the fluorine, oxygen, or nitrogen. And that's the intermolecular force. Then the interatomic force is between the atoms. Tegan, can you tell me what type of interatomic force this is?
Covalent.
Yes, correct. This is covalence. Not compulsory, but guess you could specifically say it's a polar covalent bond. But that is the key difference between the interatomic forces, ionic, covalent, or metallic, and the intermolecular forces, dipole, dipole, induced dipole, or hydrogen bonding, which is again a key thing that needs to be represented on your model. I mean, if you're looking for something simple to do, this is like practically your model. I'm drawing it out. You just have to build it in 3D. If you just cut out like pieces of cardboard, just saying that there. This needs to be represented. Okay, question 5, I think. Use liquid ammonia NH3L as an example and answer the following questions. Someone wrote something in this textbook. Use a diagram to illustrate what happens when the intermolecular forces of ammonia is broken. So what I'm doing here is what the particles in a liquid look like. It's taking you back to phases of matter. In a liquid, the particles are in no regular pattern, but they're still quite close together, like water filling a container. So if I'm showing the molecules in NH3, it's a similar diagram to the one above, where I'm using a solid line for the covalent bonds, and the hydrogen bonds, intermolecular force rather, will be between the lone pair and the hydrogen. Hydrogen and a lone pair. I'm not so much considering the geometry and the shape of the intermolecular force. NH3 does have to be this trigonal pyramidal side, so we can see there's a lone pair. But when the intermolecular force is broken, that's this dashed line here, I'm drawing a cross over it to show that's what happens when the intermolecular force is broken. So if this is starting off in my liquid phase, when we overcome that intermolecular force, not break it, overcome it, those particles can now escape into the gas phase, where they will be very far apart. And when they are very far apart, I will still have my ammonia molecule with its covalent bonds, but that intermolecular force will no longer be there because the other particle is so far apart, and you won't have an intermolecular force stretching over such a great distance. So this is one representation of how I would answer 511. Here's the intermolecular force that is there in a liquid. When it's a gas, the particles, the molecules are too far apart to form that intermolecular force. But a key thing, the covalent bonds stay as they are, because that's 512. So 512 is now trying to illustrate what happens when the interatomic forces of ammonia are broken. Interatomic, in between the atoms. So this is my ammonia molecule. If I'm going to break this interatomic force, I guess simplistically you would draw something like this and just cut it off that way, but this is not something you would find. There's no such thing as NH2 and H just by themselves. What would happen is that this NH3 would break up into its elements nitrogen and hydrogen. Can someone tell me why did I put 3 lines there? Why are there 3 lines between these nitrogen atoms?
So it's because they share 3 bonds with each other, the 3 valence electrons.
Electrons, yes, exactly right. When nitrogen is bonded to itself, because it's diatomic, it has a valency of 3, so it forms 3 bonds with itself. Okay, so I wouldn't expect anyone to take NH3 and break it up into the elements. In this question, they're just asking you to see, or asking you to see, that if you break the interatomic forces, you break up the molecule and make something different. Just to show the difference between the interatomic or covalent bonds and the intermolecular hydrogen bonds. I hate saying the word bond when I'm talking about an intermolecular force. All right, for question 5.2, explain which of the process this or this requires more energy. So to explain why is actually not an easy thing. To say which one is a lot easier. But if anyone tried it or thinking about it now, which one do you think would require more energy?
So I would say interatomic.
Yes, interatomic is correct. Would you dare to try an explanation why?
So I can try. It's probably wrong, but my thinking was like the interatomic are like bonds, whereas the intermolecular are just forces of attraction, which will need less energy to overcome, like with phase changing.
I suppose I would give that some credit. I mean, I would also say the same thing as you in that I might also be wrong when I say this, but they're both forces of attraction. But to say that the interatomic forces are just stronger forces of attraction, therefore they require more energy, I think is actually getting away with the explanation, and I would give you the mark. I think you did say something about that. Saying that you have a stronger interatomic force, because they are both forces of attraction. Even an interatomic force is an attraction between the electrons of the two atoms. So by saying that you have a stronger attraction, and this is an idea to write down that will apply to any explanation, is that if you have a stronger attraction, you require more energy to overcome it. And interatomic forces have a stronger attraction. I think that is sufficient. Of course, you might be thinking, well, why is it a stronger attraction? And that's where it now becomes technical. And I would almost say I'd be guessing if I say that it's because, or I would think it's because these atoms are a lot closer together than the molecules are. It's over a much shorter distance. You have a lot stronger charge between these atoms because there's a whole electron being shared. Whereas if we talk about the intermolecular force, well, that's not between a whole electron, that's between a lone pair and another atom over a much bigger distance. Okay, but I think it's sufficient to just say, because this textbook only gave you 2 lines, that interatomic forces have a stronger attraction, so they have more energy to overcome. Okay, then question 8, the ticking of boxes. I'm going to try and draw. All three things look like a pen. Is this a pen? Yes. Okay, so the first one's done as an example to show you that HCl will have induced dipole forces. And that's giving you a hint that every single molecule is going to have induced dipole forces, so long as there are electrons. So I chose this exercise, so ticks for everything there. When it comes to the most important or strongest intermolecular force, that's where you have to consider all three. Okay, so without any thinking, I can say all of them have induced dipole forces. Then to decide if it has dipole forces, I need to ask myself, is this molecule polar or not? Now, you don't have to go through, I hope, well, it would be good if you did, go through all the steps for each of these molecules to determine if there's polar. You draw a Lewis structure, you determine the shape, you look at the electronegativity, and you look at the symmetry. But it's enough to do that thinking in your head. H2 is not a polar molecule, so there's no dipole forces. Dipole forces only happens if you have a polar molecule. Then, does it have hydrogen bonding? There's plenty here. I'm going to ask each person one compound. Bianca, for H2, does it have hydrogen bonding? Yes or no?
No, sir.
No. For hydrogen bonding, we need to have hydrogen, obviously, and fluorine, oxygen, or nitrogen. Common thing is if, you know, I'm like exaggerated here, don't learn the work and then you just see hydrogen bonding and you think it must be hydrogen, this is hydrogen. No, hydrogen does not have hydrogen bonding. And because of that, the most important or the only intermolecular force is the induced dipole. I can't write with this pen on a cold day. Imagine I had to mark exams like this. How sad. Induced dipole. Right. It's the only one anyway. Right, the next one, H2O, this example that eventually you get sick of seeing it, but maybe comfortable because it's one that you do know. Right, Christopher, I'll ask you for this one, H2O, dipole forces, yes or no?
I said yes, sir.
Okay, that's correct. Hydrogen bonding?
Yes, sir.
And the strongest intermolecular force?
Hydrogen bond.
Is hydrogen bonding, correct. Okay, so this is also a useful one to show you that apart from it having induced dipole forces and hydrogen bonding are related to each other. I mean, if you think about it, hydrogen bonding is just a special dipole force, like I mentioned. It just happens to be super strong. But as a matter of classifying them, we would tick both boxes. Okay, the next one, Emma, CH3Cl. Dipole forces, yes or no?
So did you say my name?
Yes, Emma.
I said no and no.
No and no. So why did you decide it doesn't have dipole forces?
Because
think the
it's
text-
not polar. Or did
Textbook
I
does
calculate
contradict
wrong?
itself. Well, even without a calculation, in the textbook, in one place, it says CH3Cl is non-polar, and then in a whole page, I think I was looking at it yesterday afternoon, it says that it is polar. Okay, but even without the calculations, if we just look at the shape of CH3Cl, it's tetrahedral, but we know that chlorine has a bigger electronegativity than carbon. So just by looking at it, we can see that the electron pull is not going to be equal anywhere. I mean, you could look at the values here. Yesterday in class, I looked at something that was, yesterday I looked at CHCl3. This is similar, not the same thing, but the electronegativity differences are not zero. So we have polar bonds, and those polar bonds are not equal in all directions. So this is going to be a polar molecule, very weakly polar though, might I add, like very, very weakly polar. Which is why the textbook does call it a non-polar molecule in one place. But the differences are 0.4 and 0.5. 0.4 for the hydrogen and 0.5 for the chlorine. That makes this a polar molecule, so we have dipole forces, but you're right, there are no hydrogen bonds. And the strongest intermolecular force, Emma, in light of this, which would it be?
I said induced dipole.
Okay, if you didn't have dipole forces. Dipole forces are stronger than induced dipoles. So if you did see there were dipole forces because it's polar, the strongest intermolecular force is dipole forces.
Oh yeah,
So that
just
was
because I got it differently.
yeah, exactly. Yeah, you see it that way. That was looks like one of the trickier ones there because you have to analyze the shape carefully. All right, the next one, Ne, Gabby.
So I said no and no, and then the strongest is induced dipole.
Yes, I'm just going to, I can't write, I'm just going to say 1 where this is 1. Right, so neon, noble gas has induced dipole forces and strongest force is induced dipoles. Also, one of the easiest, not one of, the easiest thing to do for your project. Now, if you just want to get it done, do neon. It's literally just one atom attracted to another atom. No need for shapes and things. And that does suffice. All right, the next one, NH3, another familiar favorite. Hannah?
So I say yes and yes.
And the strongest?
Strongest is hydrogen bond.
Correct. The next one, Hassan, have you done HF? Hassan, are you here? Can you hear me all right? Okay, I'll come around. Jared, HF? Jared, I can't hear you. Okay, I'll come back to Jared with that question, or, well, he's rejoining.
Can you hear me now?
Yes, Jared. So, HF.
So is it yes, and then the strongest would be hydrogen bond?
Yes. Yes, yes. Hydrogen bonding, yes. Okay, the next one, C2H2. Kaylee, unfamiliar one. C2H2.
I said yes, no, and then it would be dipole.
Oh, so you said yes? Are there dipole forces, yes or no?
Yes to dipole forces, no to hydrogen bond.
Okay, so there are no dipole forces, and I'll show you why. Is if you drew out the structure of it, did you get something like this? C2H2. I'm just trying to think how else would you see this? Yeah. Katie, did you draw out the shape of C2H2 to look something like this?
No, it didn't look like that. I think that's where it
Because
went
that was a trickier one. So C2H2 will have a double bond between the carbons and hydrogens on this, sorry, C2H2. It's not that shape. The only way you can have C2H2 is with a triple bond and a hydrogen on each side. Did your shape look like this? Kaylee?
No, still no.
Okay, it was a trickier one, but that's the only way you can bond 2 carbons and 2 hydrogens together with a triple bond between them and a hydrogen on each side. Now, if I had to just throw in some VSCPR and I look at this carbon on, so firstly, in terms of the electronegativity difference, we are going to have a double on the left because there is an electronegativity difference between carbon and hydrogen, nothing between carbon and carbon. But you have to look at the shape as well. What type of shape would you get around this carbon atom? What type of shape do I have around this carbon atom? Kaylee?
Linear.
Yeah, well, Jared, yes, this is a linear shape around this carbon. Because around that carbon, it has 2 regions of bonding electrons, 2 bonding pairs, and 0 lone pairs, and that will have to be linear. It also only 3 atoms. So this is a linear shape, and therefore it is symmetrical. So it's a non-polar molecule, no dipole forces, no hydrogen bonding, because there's no fluorine, oxygen, or nitrogen, and the strongest force is induced dipoles. All right, next one, Nick, CO2. Nick, CO2, are you there?
So I said no and no.
You said no to dipole forces and no to hydrogen bonding. That is correct. Another familiar example, one we've done before. Sorry if I keep saying it, but it feels like I've done it before. CO2 has got dipoles, but they are symmetric, so you have a non-polar molecule. Okay, if I compare that to CO, Tegan,
So I said yes, no, dipole, dipole.
correct. So there is dipole forces, there's no hydrogen bonding, and the most important force is dipole-dipole forces. Just a reminder that with CO, you have a triple bond. That third bond comes from the oxygen. It's that dative covalent bond. All right, then Trifluso Cl2.
So I said no, no, and then induced dipole.
Correct. So there's no dipoles, there's no hydrogen bonding. Most important is induced dipoles. The next one, Zama CF4.
So I said yes and no.
It's no and no. I'll show you why. I just want to draw this one and the last two. Okay, so with CF4, another one that's not immediately obvious. So to determine the type of intermolecular force in CF4, start with your Lewis structure. Now, even without a calculation, you know that this is very electronegative. We are going to have a dipole. But the dipoles will be symmetric in all directions. This is a tetrahedral molecule, 4 bonding pairs, and they pull in equal directions. So overall, this is a non-polar molecule, and non-polar molecules do not have dipole-dipole forces. Okay, so for CF4, there are no dipole-dipole forces. There's no hydrogen bonding. So the most important force is induced dipoles. Okay, I'll draw the last two, which are CH2Cl2. These are, I don't know, interesting exam questions or just challenges. Problem solving. Okay, so this is what CH2Cl2 would look like. It's similar to that CH3Cl, the one we did yesterday. We have the same idea. We have an electron pull towards the chlorine. That difference is 0.5 and hydrogen is 0.4. Even though that's the difference, make sure that you look at which one is more electronegative. Because here, with a difference of 0.5, electrons are pulled towards the chlorine. Here, with a difference of 0.4, electrons are pulled towards the carbon, because carbon is more electronegative. It's not necessary in this question, of course, to draw all of them. This is just to show you that overall, the pull of the electrons doesn't cancel out. The textbook describes it as an asymmetric distribution, which is big words. Basically, the dipoles don't cancel each other out. So this is a polar molecule. We have dipole-dipole forces, no hydrogen bonding, and dipole-dipole is the strongest intermolecular force. And then my favorites, what is this? This is det, I think. I think it's det. CH3 O CH3. Is there anyone who was intrigued enough by the problem and was able to get to the structure? Just curious. Did anyone get to this? There's a reason why it's the last question. Okay, it's called DET because this is something known as diethyl ether. It's a very sweet-smelling but toxic chemical that will kill you as soon as it enters your lungs. Well, not as soon as, but it's poisonous. That's my line. That's the point I'm making. Right. So if we think about the electronegativities and the pull of the electrons, because you've got quite a big molecule here, hydrogen and carbon have a slightly polar bond going this way. Oxygen, we know, without even looking at the table, will have an electron pull towards it on both sides. And if I have to look at the overall shape, it's difficult to convince you in 2 dimensions here that the pull of the electrons is overall balanced, meaning they cancel each other out. It's symmetric. We don't have any part of this molecule that will have more electrons than the other. And you might be thinking of this I'm hesitating here. Actually, sorry. Even though it looks like they do cancel each other out, it's a very technical thing. Remember that when I draw water as a bent shape because it has a lone pair, right? I mean, water looks like this. In this case, instead of having hydrogens there, I've got this CH3 thing. So if I had to try and draw the shape realistically, it wouldn't look like it's in a straight line. It would have this bent shape around the oxygen. Do not forget the idea of these lone pairs. So now my question, looking at the molecule in this shape, do you think this is going to be a polar or a non-polar molecule? Anyone? Answer? Opinion? Yes? No? Shout? Or just agree? Thank you, Chris. So Christopher agrees it is going to be polar. I don't know if agree means polar, but anyway, this is going to be a polar molecule. Because of the bent shape, the electrons are going to be pulled more towards this top end. So I will have a delta minus on the side. That means everything on the other side of the molecule will be a slightly delta plus, because a dipole must have 2 opposite ends. And so this will form dipole-dipole forces, no hydrogen bonding, and the strongest intermolecular force is dipole-dipole forces. Okay, but there's a reason it's the last question, so if you didn't get to this, don't work yourself to a frenzy. And in terms of a project, this is a reasonable idea for using on that project. If paging through this textbook, there are lots and lots of different molecules to use, some simpler to use than others, but this is something reasonable that could work and not as boring as neon. Oh, that was question 8, and the rest, the numbering in this textbook is just going mad. Anyway, so that's the end of that question I asked you to try. Maybe you've tried more than the next question, but I want to look at the last of those slide things, and then I'll return to 2 more of these problems. Okay, so there's absolutely nothing new to write on here. I was writing on my book and using those as examples, because with this chemistry section, it's a lot easier to be writing than just going through these slides. Anyway, I'm just going to go through them because there are some interesting pictures here. So we already discussed and wrote down a few of these ideas about hydrogen bonding. Note, there's no definition you need to know for it, just the conditions which we wrote down about hydrogen and the lone pair. That's what LP was for. We looked at these three examples, but what I have here are some very pretty pictures from the internet showing you the shape of the intermolecular forces. Now, we would never expect you to be able to draw water in this perfect geometric pattern. You know, some perfectionists are able to do so, but it's showing you the idea I was going over yesterday about how the number of lone pairs will affect bonds I can form optimally. In this first picture here, of course, it's possible to have an intermolecular force with this fluorine on all three sides and make it appear to have 4, but that's not going to be possible because we have 3 lone pairs and 1 hydrogen atom. So if I keep adding HF molecules, eventually I'm going to have too many lone pairs and too few hydrogen atoms. So that is why, and went over this in the sport lesson yesterday as well, that is why in hydrogen fluoride with 3 lone pairs and 1 hydrogen atom, we can only form 2 hydrogen bonds on 2 sides. With water, there's 2 lone pairs, 2 hydrogens, and we can form 4 hydrogen bonds. With NH3, there was 1 lone pair, 3 hydrogen atoms, and we can only form 2 hydrogen bonds. There'll be a hydrogen left over in that case. And being able to count the exact number is not the emphasis here. The emphasis is to explain why water has such strong intermolecular forces. Experimentally, water has the highest boiling point of these 3, even though their molar masses only differ by just 1. I mean, even if we just look at their molar masses, this has, HF has the most, I think. Yeah, we looked at it yesterday. HF has the biggest molar mass, but it doesn't have the highest boiling point. H2O does. And that's because it has more places for hydrogen bonding to form. As I ended yesterday, without that simple fact, life as we know it would not exist because water would not be a liquid at room temperature. Okay, so this page is just showing you more detail about the intermolecular forces in water. So the question I marked in the homework about the difference in a liquid and a solid is, I guess, related to this. So what we have here is we have a picture of liquid water and a picture of ice. So you might know, you will know, you have to know, that if you put ice on water, it's going to float. But have you ever investigated or been told the reason why ice floats? I'm just curious because it's very often that grade 8 teachers lie to their students about why ice floats or misrepresent it. Anyone know, why does ice float? Never wondered why ice floats. If I told you it's because the ice is cold and it wants to be nearer to the sun, so it rises to the top, would you accept that? Maybe not. Anyway, what is misrepresented is when we draw particles in a solid, we draw them as closely packed. And when we draw them in a liquid, we draw them spaced out. But that is not true of water, which is one lie that happens with phase change. If we look at these pictures here, in liquid state, the water molecules are closer together overall. And the reason that they're closer is because those intermolecular forces, that's these black lines here, that hold the molecules together, individual molecules, break and form because the particles are constantly sliding over each other. So by having that force break and then form again, break and form again, overall the molecules are closer together, and that is what affects if something floats or not. Do you remember the word density from grade 8? Or was density nothing more than this formula? D equals m over v. Yes, no? Zamba, did you do density in grade 8?
No.
No, okay. Well, I don't know if these guys did. Tliso, did you do density in grade 8? I can't hear you, Tliso. Your connection is not looking good my side. Nick, did you do density in grade 8?
Sir, I do not remember that far back.
It's like, what, 3 years back? How can you not? 3 years back? No, that's not a good sign. Well, in any case, even if you don't remember, it's not a significant thing. We're not going to ever look at a calculation like this. The idea is that if the particles are closer together, we say they are more dense. And if something is more dense, it's going to sink to the bottom. So what these two pictures are showing you is that in ice, the particles are actually further apart in a way. There's these huge open spaces, like a cage. So overall, if I had to take the mass of this area, it's going to be less dense than the liquid water. And since ice is less dense, that is the reason why it floats to the top. So maybe now you get a better idea why does ice float. And again, this is just as an important point as hydrogen bonding, because without the simple facts that ice floats, life as we know it would not exist. If you know how life formed on Earth, or how it exists on might exist on other planets, if ice didn't float, I mean, take fish for instance, then lakes and oceans would freeze from the bottom up. And if they froze from the bottom up, you would not have, well, how do I put this? The fact that ice can float, if you take an ocean or a lake, when ice freezes at the top, you still have liquid water underneath that has got oxygen trapped inside it, oxygen in the water. And you have an entire ecosystem with fish and life that live beneath the surface of the ice. And in science fiction, or actually science facts, this is speculated as to how life is present on frozen oceans on the moons of, I think, Europa and Io. Those are moons on Saturn. That there are frozen lakes, frozen oceans, under which there may exist life. So here's something interesting behind this. Chris, do you believe in life on Saturn and Jupiter, in the frozen moons? Do you believe life exists out there? Also, can't hear you. Audio not coming through. Sometimes I wonder, sitting in these online lessons, if life exists. And I hear some sounds and I have belief again. Anyway, so this is just some thing about why liquid water is less dense than, liquid water is more dense than ice. Okay, this idea of surface tension is something that used to be done in grade 8. It's not very often done. It's a small detail that links to the physical properties of intermolecular forces. So I'm telling you, I do the same slide in grade 8. How many of you have seen this insect before? Has anyone seen this insect? Just a show of hands. Have you seen this creature? These water striders, creepy things that seem to walk on the surface of swimming pools and dams. Well, I don't think I've ever seen them on a swimming pool, especially never school pools, because school pools are just dumped with chemicals. I wonder what the condition of your school pool is like after 2 years of not being used. But anyway, the reason why these creatures can walk on water is 2 reasons. Firstly, they actually have something non-polar on their feet that repels against the water. But the idea that I'm coming to in the slide is about surface tension, and surface tension is nicely showed by this picture on the right. So we know that water molecules have an attraction between each other. That is hydrogen bonding. Now that attraction is so strong that it's actually able to hold the surface of the water together. So if I put something like an insect on the top, that insect doesn't have enough weight to force itself through the water and break the surface of the liquid. So surface tension is caused by the attraction of water molecules. Again, there's no definition for it, but it's one property that makes water special. Water is our special chemical. And an easy way to demonstrate this is a tap dripping. And if you ever played with a tap, that when a tap drips, it comes in very specific droplets. You have to try the same thing with any other liquid, like sanitizer. I guess that's our second favorite liquid. Sanitizer or oil. It's not going to form individual drops. It's going to form a stream. So the reason why it forms drops is because water has the ability to stick together into one individual drop. So I think I did have something that I was showing to grade 8s to just demonstrate surface tension. This is I hate saying it's a grade 8 experiment, but it's just one way to see this, and I think I'm going to end there. So I have here a piece of glass that is a phone. Now if I put some water on a phone, which is not something you should do, you can see that the water is causing these very specific droplet shapes. You get a better view of this from the side, or when we return to school on Monday, I'll show you another thing with surface tension. But an interesting thing is my phone doesn't switch on by itself. Is if I try and spread out this puddle of water, watch what happens when I take my fingers away. So if I had enough water, literally pouring water on this phone. If I spread out this water, as I take my fingers away, I want you to look very carefully. Can you see that this puddle is kind of pulling itself back together?
So we can't see
But you can't see anything.
We're supposed to be watching.
I guess that's a good thing. I guess it's a good thing because there's just a lot of water everywhere. Sorry, I didn't click this share button. Okay, so now all you see is a very wet phone. This works nicely on glass because glass repels water. So doing some crazy, pouring a lot of water on this phone. Now if I spread out this water with my fingers, can you see that as I let go, the water is seeming to pull itself back together? Or am I doing some magic here? So where's that water going? How is it disappearing? Anyone? Where's that water being pulled into? It's like magic tricks here. Spreading out the water and it's getting smaller. Any ideas? Where's that missing water going?
So isn't it just
I'm
going
showing
to
you.
the main one that has the most water? I don't know if I'm right though. I don't know.
Well, it is going that way, but then why is the puddle not getting bigger on the side? I'll show you magic tricks here. Where's that water going? I think I should retire from this and become a magician. Anyway, so the water is being pulled that way. The reason you can't see where it's going is because it's rising vertically. If you had to look at this from the side, it's quite amazing that the puddle actually stands up to quite a great height. But the reason the water is pulling together is because of surface tension. There's an attraction between the water molecules that is so strong that pulls it together. And the surface tension is somewhat so great that if I take something very light, like a staple or piece of paper, it can nicely float on the top without getting totally soaked. If you can see very carefully, you can see that the paper is making like tiny impressions on the water, pressing into it, showing that the surface tension is supporting the water. Okay, but that's the last thing on surface tension, the last slide on there. The rest is just a meme. But surface tension is an important application of the intermolecular force of water. Okay, so before I end they tell us that we shouldn't teach in the second lesson of a double because we need breaks, because online makes you tired. It's not online that makes you tired, it's the fact we don't have much to energize ourselves. Anyway, what I would like you to do though is the rest of those exercise questions. You all still have the numbers from yesterday, I hope. Before I get too much water on everything. Okay, I'm still going to stay in this meeting, but you don't need to. Give me the rest of this time now to work on either, I don't know how you would work on your projects. I can split this meeting up into breakout rooms, or be working on those exercise questions. Should have the page numbers here. Yeah, so we've done 5, we've done 8, but up to 13 and page 16, number 7 and 11. Please be working on those questions now. It's on intermolecular forces. But that is pretty much the end of the chapter. And next week, I'm going to hopefully just be marking the last few of these exercises and then starting on the next section. All right, so I'm ending my recording and the lesson here. I'll stay in this meeting if you still have any